There we go, great. All right, we will continue recording for the next couple of classes because we were missing a few. So today is the last day of material that will be on your first exam. So two major things that we're going to do today. First one, exponential functions, and then the second part of class, logarithmic functions. So, the question is, what is an exponential function? Well, we know what a polynomial type function is, right? Y equals x to a power, particularly x to a positive integer power. Parabolas, cubics, things like that. And we can do sums of things like that. Very easy to work with in a calculus sense, very easy to take derivatives of. But an exponential function is anything of the form f of x equals a to the x power, where a is greater than 0 and a is not equal to 1. In other words, a is a real number. A is not a variable. So 2 to a power, e to a power, right? 10 to a power. That's what an exponential function is, and it has a very, very different look and different feel. And the calculus of exponential functions is quite different than it is from polynomial functions. I have a black pen. Did I take it? Ah, here we go. So, if I were to draw a graph of an exponential function, we know that if I raise it to the 0th power, I'm going to get a 1. So that they generally will always intersect at 0, 1. And if a is bigger than 1, then it basically is going to do that. And then on this side, that. Now, what value of x will produce 0? It'll never be 0. But if I put a large negative in for x, that's right, reciprocal to a positive power, it's going to get really small really fast, which means that I have a horizontal asymptote here for the x-axis. This would be the case where a is greater than 1. And this is generally referred to as exponential growth. Everything alive kind of works this way. We're going to talk about money in a little bit because that's a little bit different, but like world populations, things like that. Now, what if a is small, like a half or a tenth? A cannot be negative, otherwise a lot of your outputs, most of them would be imaginary. Okay? So if a was small, like let's say a half, then I go the other way, because as it gets larger and larger exponent, the value would be smaller and smaller, and they actually look like mirror images. The blue graph is an example of what? If the first one's exponential growth,
exponential decay.
Decay. And what works this way? Well, everything that's dead. When things die, they decay, and they decay exponentially. And it's a really simple way of saying nothing ever is really gone. But the amount left is so small I might not notice. So we use these to do a lot of things, right? Not just in math, but in physics and biology. You remember that question in algebra, right? The bacteria in the petri dish doubles every 4 hours. So, you know, what's the population in 10 hours, 20 hours, 30 hours? Well, if I had the model, it's really, really simple. So then what happens? The bacteria just keeps growing and growing. Eventually, petri dish explodes, the bacteria takes over, eventually the whole earth is covered and we're all consumed. Right? But that doesn't usually happen, does it? At least not often. So what happens to the bacteria in the petri dish? We have to understand from science, it dies because what? Two things. It runs out of food and space. This is an absolute. So when we talk about exponential growth, it's always over a finite interval of time. You can never express it over an infinite amount of time because things cannot grow infinitely because there's not unlimited resources, there's not unlimited space. So literally, planet Earth, there would be an upper limit of how many human beings could really survive. I don't think we're very close to that yet. But the idea is, if I know how fast a population is growing, then I can predict the population in the future. This is a major problem that we do at the beginning of Calc 2. We talk about exponential growth in terms of populations. But it's only for a finite period of time because it's not going to continue to grow at the same rate forever. But we do know certain things do grow at a constant rate forever. For example, the crystal that you're growing in the lab is going to grow at a constant rate. We know that decay of certain things like carbon-14 and things like that, we know it's constant, so we can measure things like this. This is very important. This is why we study exponential functions, because we can predict certain things, certain behaviors. So something like radioactive material, right? Depending on the isotopes and stuff, we know how fast it's going to decay, so we know when it will reach potentially a safe level. Now, that safe level might be really far off in the future, or it might be really, really fast, right? There are elements that are so unstable that we talk about things in nanoseconds. So if I have something and it's growing, then let's say I can ask when will I have twice as much stuff? That's called the doubling time. If it's decaying, it's the same question, when will I have half as much stuff? And that's called the half-life. That's what that term is. Oh, it has to be decaying to have a half-life. If it's growing, then it has a doubling time. These are things that are really easy if I already have the model. We're interested in the calculus. And so we're not interested in all exponential functions. We're very specifically interested in one particular one. So here's what we're going to do. We want to talk about money growth. Okay, so this is what is called periodic growth. That's how money grows. Money does not grow continuously. Populations grow continuously. Meaning, since the start of class, the world's population has actually changed. But since the start of class, the amount of money you have in your account has not. See, if money grew continuously, then when you go to the bank to withdraw money, you say, oh good, there's a long line. So I'll have more money when I get to the front of the line. Now take your time counting it out. It doesn't work that way. Money grows periodically. It could be daily, it could be monthly, it could be annually, but it is over periods, so it will not change during that period of time. So periodic growth, which is how we start this concept, this is how money has actually grown for thousands of years. Most of you learned this in baby algebra class, right? Accumulated amount, principal, R is the rate as a decimal, N is the number of times that you compound it per period of time, T is the period of time. Usually this is measured in years. It doesn't have to be, it's usually measured in years. So if you have just an old-fashioned savings account and you get interest every 3 months, quarterly, that would mean N is 4. That's it. If, how many here, does anyone here pay a mortgage? Okay, how often is your mortgage interest calculated? Monthly. Well, believe it or not, it's daily, but you pay it monthly. How about credit cards? Same thing, daily, but as long as you pay off your balance monthly, you don't have any interest. But if you're not paying off your balance, then paying a payment a little bit early will save you a little bit of money. But those are actually calculated daily. But your savings and things like that are calculated usually more long-term, maybe quarterly or monthly. It depends on the account. So we want to be able to manipulate this, so we're going to make this really simple. Okay, I've been catching up on my old Sopranos episodes, and I realize, engineering it's a good route. That's a really good, safe route. But if you guys really want to make some money in life, there's only one way. You got to become loan sharks. Okay, so we're going to start our first, Math 150 loan shark industry, and of course, all of our loans. We're loan sharks, right? All of our loans are going to be $1 million. And of course, this is the ultimate oh duh. What's our interest rate going to be? 100%. Come on, we're loan sharks. So we're going to make it really easy. We're going to use interest rates of 100%, and we're going to make $1 million loans. Okay? So now the question is, and by the way, 1 year is the total duration we'll ever deal with. So how many times should we compound it? So you're going to be the bookkeeper, right? So you're going to do that, and then you're going to be the person who emails the people, okay, we want a payment, now, or we're going to send somebody out to, deal with your legs. You guys know what I'm talking about, right? If you don't, just look it up. Yeah, it's not pleasant if you're late on a payment. So, how do I set up this equation then? Well, if the principal is $1 million, and the interest rate is 100%, and the loans are only going to be for 1 year at a time, then I basically come down to this, don't I? If T is 1 and R is 1, then I have this. So here's what we're going to do. Get out your calculators, please. We're going to calculate. Now, we're rookies in the loan shark business, so we really don't understand the concept of compounding. So we're going to loan you $1 million, and you're going to pay us back in 1 year. It's not going to be compounded at all. You're just going to pay us back in 1 year. So in other words, N is 1. Well, that makes it easy. If N is 1, then you're going to pay us back $2 million. All right? But you know what? Even banks do better than that. So let's suppose we compound 4 times per year. So what's the difference in the payback now? So now we're going to use an n of 4. So you're going to have 1 plus a fourth, and then raise that to the 4th power. Now, this is significant, folks. Now what's the payback? All you need is an n 25 cents, by the way. We're loan sharks. We don't just forgive the change. Right? You know, you only give me 24 cents, you know, might break a fingernail. Okay. Well, what if we did it monthly? And 29 cents. Wow. Well, from quarterly to monthly, we made more money, but only about 170,000, a little more than 170,000. Okay, we're not messing around. Daily. Let's go daily, right? So you're going to be sending out lots of emails now, right? And you're going to be knocking on a lot of doors and calculating. So we do this 365 times a year. Oops. That's 2,714,567 and 48 cents. Yeah, cheap calculator's better. It literally takes about 4 seconds to do the entire calculation. Now, we went from monthly to daily. That's more than 30 times more. We got more money, but do you notice that increase wasn't huge, was it? Really, really slowed down. Okay. Oops. We're going to have fun. We're basically going to go every hour. Every hour. That's insane, I know. Every hour is about 500,000 times per year. Technically, it's 525,600 hours. I'm just going to make a nice round number. We're gonna do this. So every hour you're calculating, you're knocking on their door, you're banging on the door. You know, if they don't pay you, that installment, right? You're getting, okay. So what does this come out to be?
At that point in time, I just £600.
Hold on. There we go. All right, now, but this is out of control. Now it's, we're doing a lot of extra work. We're now doing this every hour, basically, and we're still increasing our money, but it doesn't really seem to be increasing very much, does it? In other words, we're kind of locking in digits, aren't we? The changes are starting to happen where? Further and further out, too. Okay, every hour. Oh no, every second. Okay, so you're just constantly doing the calculations, okay? So let's just say for fun, instead of 500,000, okay, so 365 times 24 times 60, that's hourly. This is minutely. This is secondly. There's roughly 2 billion seconds. Roughly 2 billion seconds in the year. Right? Yeah, we're gonna do it. We're gonna do it every second now. So you're never leaving. You're just camping up and knocking on the door constantly. So let's do this every second, quite literally. Okay. And I got so much more money. I got an extra $2.72. If I just kept going, eventually the change is going to be in the penny, and eventually it might not even change. How interesting.
Not worth the manpower.
Are you guys seeing something here? Do you see a number here? If I take out the million, what am I multiplying the million by? 2.7 something. This is by far the most important math number, science number, chemistry.
Oh.
The most important number there is E. Far and away the most important number there is. E is, on my calculator, if I do E, on my calculator, oops, there it is. E is approximately, E is an irrational number. It's approximately 2.7182818. Wait a minute, that's, if I said round E off, that's a million times E, isn't it? Interesting. So if I take out the million, see this part right here? It's looking a lot like E as n gets bigger and bigger and bigger. You smell it? It smells like a limit. Oh yes. E is defined to be the limit as n goes to infinity of 1 plus 1 over n raised to the nth power. In other words, as n gets bigger and bigger and bigger and bigger, this quantity approaches E. It's always getting bigger, but the changes occurred later and later and later and later until when my n is so big I don't even see the changes anymore. The number on my screen, for all practical purposes, was a million times E, wasn't it? But you know, I had to use a really big. Okay? This is continuous growth. Periodic growth is like interest. I compound it every so often. But populations, you know, grow continuously. How do you know populations grow? Well, because you don't all have the same birthday, for one thing. Right, we're only going to all be born once per year, and we're all going to die only once per year. So if you don't die then, you got to wait till next year, right? If you're not born now, you got to wait till next year. Well, it doesn't work that way. People are continuously coming and going on planet Earth, right? It's constantly changing. There's no time intervals. So all growth and decay are actually continuous. Periodic is how we started easily, but that's where we're headed. So E ends up being this crazy, crazy limit. And it turns out to be the most important number because it shows up, pretty much shows up everywhere. But a lot of folks don't know where it came from. It's actually equal to this limit. We will work with this extensively in Calc 2 and the limit part of it. So I'm interested in the calculus of E now. So here's the function we want to talk about. Excuse me. We want y equals e to the x. So now we already know what it looks like. E is a number between 2 and 3, so we know it's going to grow. Okay? What I'd like to do is figure out the derivative of this. Now this is an interesting problem. So I'm going to just a moment. I'm going to bring this up on Desmos in a second. Okay, so I'll come back to this in a moment. So we want to see the behavior of E. We know E is exponential in nature, so we know certain things about it because it's growing, but what we're interested in is the rate of change. Because E is such a common value, e to the x is a very, very common function. So this looks like exponential growth, right? We just did this a moment ago. Now you see how it passes through 0, 1, boom. I'm interested in the slope of the tangent line at this because I'm interested in the instantaneous rate of change, the derivative, for anything involving an E. So let's start with dy dx, right? The definition of the derivative, this is the limit as delta x goes to 0 of e to the x plus delta x, because that's f of x plus delta x, minus e to the x. This is what I'm interested in. Okay? I would like to take this limit. Is there any algebra I can perform on this? Look at the first term.
Natural log?
No. I just on the exponential part. Just think exponential. Is there any algebra I can perform, particularly on this part? Think rules of exponents.
You can subtract the x from 1.
In other words, if I said x to the a plus b, isn't that x to the a
Times x.
times x to the b? So can I do something with that right there? Yeah, that's what I'm looking at. Can I manipulate that? When we did the sine and cosine last week, we used the expansions to be able to factor things out. So if I expand this, that's going to be e to the x times e to the delta x minus e to the x over delta x. Can I now factor an e to the x out of that? Yeah, and that's a good thing. So this will be, in fact, the limit as delta x goes to 0 of e to the x times the limit as delta x goes to 0, what's left? E to the delta x minus 1 over delta x. Well, I know what the answer to this one is. Right, there's no delta x, so this is just going to be e to the x. That's the one we're interested in. What does that look like? And I'm not going to try to plug in numbers and see if I can see behavior. So instead, let's consider it this way. Delta x is my argument. It wouldn't matter what symbol. I could say e to the t. I could say e to the y. I'm saying e to the delta x. If I asked you, I'm going to ask you a similar question. Is this the same thing as that? I have delta x going to 0, and that's a delta x, and that's a delta x. So think of it as thing is going to 0, e to the thing minus 1 divided by thing. The reason I want to do this is because I can graph this one on Desmos quite easily.
Wait, sorry, what did you do right there?
Well, I'm just saying, let's make our argument x rather than delta x.
Okay.
Remember, what did we prove? We proved the limit as theta goes to 0 of sine theta over theta. It's the same as the limit as x goes to 0 of sine x over x. The limit as t goes to 0 of sine t over t. Right? They just have to be the same argument. So if my argument here is thing goes to 0 of e to the thing minus 1 over thing.
Okay.
As long as this, and this are the same, I can put any symbol in there. But I want to put an x in there, not for this, for this. Desmos won't be able to graph it unless I put an actual variable in there. So let me go back to here, okay? Okay, now, this isn't a proof. This is not a proof. I've just graphed this quote. Now, would you agree that there is clearly a discontinuity at x equals 0? It's in the denominator. But when we did sine x over x, it sure looked like it was continuous. Remember, we kept zooming in and it looked like it was continuous. So clearly the discontinuity was removable. Remember, there's exactly 4 types of discontinuities. Clearly it's not asymptotic. Clearly it's not a break. And clearly it's not an endpoint. Because you'd be able to easily see those, wouldn't you? So what's the only thing it can be at 0? Removable. Because you wouldn't see a removable. So what I want to do is zoom in. I'm going to keep zooming in. I'd like to know what is the behavior of this function as x gets closer and closer and closer to 0. What is that quotient looking more and more like? I think it's kind of obvious. It sure looks like my graph is passing through 0, 1. Now, it's not defined at 0, but it's clearly a removable discontinuity. Now, I'm showing you it this way. When we did the sine theta over theta, I proved it geometrically, but we also looked at the Desmos picture to convince everybody. I cannot prove this in this class. I will prove this in about week 4 or 5 of Calc 2. We lack one tool that we will not learn until next semester. So I'm demonstrating it because we already know. We've ruled out asymptotic. Clearly endpoint's not there and there's no break in the graph. It can only be removable. And removable means I wouldn't even see the point. It looks like it's passing through it. So are we going out on a limb right now if we said we believe this limit is 1? Are you taking a leap of faith looking at that? I don't think so. I think it's kind of obvious, right? We know it's removable because the other 3 would show up graphically. So I can't prove that in this class. We're going to prove that next semester, but we can certainly accept it. Remember, I asked you to accept the derivative of x to the n until I was able to prove it? Does this seem reasonable to you based on that? It should, because it is. That is the limit. So why am I pointing that out? Because if this limit is 1, and this limit is e to the x, then what is the derivative of e to the x? It's e to the x. Oh my goosh. It is the only function that equals its own derivative. Remember I said it's a very important thing? That's a very cool thing. That makes its derivatives easier than most. The derivative of e to the x is simply e to the x. So if I go back to my first graph, I zoomed that. Okay, so now if I go back to this one and I said, let's consider any point on this graph, let's find the slope of the tangent line. The slope of the tangent line will be the same as the y value. Y equals e to the x, and the derivative is e to the x. That makes taking derivatives actually a lot easier than most things, by the way. Okay? So this is the only one I think I need the graph for today. I don't think we're going to need this after this. That's kind of a cool thing. All right, so how do we write this formally? Because last week I should say, we learned the chain rule. And we understand that most derivatives will involve the chain rule in some capacity. So I'm going to show you kind of the universal way of writing things. We know the derivative of x to the n. What if I said, sorry. Here's the implication. I'm giving sort of universal math notation. I want you to look at u, don't see a variable, see a function. I have an entire function being raised to a power. But what we usually do is we just write u. It's implied that it is u of x because I'm going to differentiate with respect to x. That means everything has to be a function of x. So we write it in this form, and then we say the derivative with respect to x of u to the n is n, u to the n minus 1, and then the chain rule factor is this. This is the way you're going to see all derivatives from now on. We're going to derive the derivative of just x, then we're going to say, what if we put an entire function in there? You know how to differentiate x to a power. But what if I said entire function to a power? Well, then it's power, function, power minus 1, derivative of function. That's the chain rule factor. So if I do this for the trig functions, instead of putting an x there, I'm going to put a u. Again, the implication is it's an entire function right there. So I know my derivative is cos u du dx. So if you look at the formula sheet that I've included in the syllabus, all of your derivatives are functions of u, not functions of x. So that means they automatically will contain the chain rule as part of the process. Okay? The derivative of e to the x is a piece of cake. But most of the time when you're dealing with e, it's going to be e to a function. It might be e to the tangent of x, or e to the x cubed, something like that. So if this is going to be the new way we always write things, then formally, how do we differentiate e to the u? Well, it's going to be e to the u. But u is a function of x. It's not just a single variable. Therefore, what will I multiply by? Du dx. Now we can throw the what if. What if u is just x to the first power? Then what's du dx? 1. So we're not violating any rules. Remember, when it's just an x, your chain rule factor is a 1, so you don't bother writing it. But if we learn our derivatives this way, then we'll never struggle with the chain rule. We just assume everything's got a chain rule, and sometimes the chain rule factor is going to be a 1. Great. Life is good in that case. Okay? So this is the new toy we have today. All right? So how would we use this? Well, we definitely can use this as product rule, quotient rule, chain rule, everything else. So let's do several examples. My goodness, we want to do lots. So I have the derivative of e to the sine x. Well, if I don't do anything else right, how about if I just write e to the sine x? Is that a good start? Now, is that the final answer? Well, I've never actually touched the sine function, so at some point I need to differentiate that. So times what?
Cos.
Times the derivative of the sine function, which is the cosine. Can I walk away right now? Yep. Does it matter which side I put the sine or the cosine on? Not really. Most people would prefer to put it in front, but is there any way somebody's going to misread that? Probably not. So I just walk away from that. Polynomials we often put in front. Again, it's just a readability thing. It's not a more correct thing. But that's it. Wow. Okay. What about if I do this? I want to differentiate, and I'm using formal derivative notation. I want to differentiate, let's say, x cubed e to the x. So this is just a straight up product rule. So walk me through. So first, times the derivative of the second. Let's see, the derivative of e to the x is, oh gosh, I can't remember that one. E to the x, yeah. That's, if you don't remember anything else, you remember that one. Okay. Plus the second times the derivative of the first.
3x squared.
I'm done with the calculus. Are you happy with this as a final answer? Well, if nothing else, you can factor out the e to the x. But what about the polynomial part? Is there anything common there?
X squared. X squared.
So what can I factor out of here?
X squared times e to the x.
And what will that leave me with?
X plus 3.
X plus 3. Is there anything else I can do, or is that it?
That's it.
That's it. By the way, does it matter what order I write those terms? No. Most of the time, if this was a solutions manual, they're probably putting the E over here. Does that make it better? No, I just leave it alone. If rewriting it isn't an improvement, then just walk away. You don't want to take a chance on actually making a mistake when you rewrite it, because that is the answer. Why is this answer better? Because I can tell exactly when this is going to be 0, which is going to be the next thing we do when we do application. Okay, done with the calculus, done with the algebra. That's the entire problem from beginning to end. Can't take more than that. If I take more than that, I may be doing steps that are unnecessary. I want to take the derivative of, how about, the tangent over e to the 2x. Ooh, make this one a little more complicated. I've written a quotient. Is there a time that I suggested that you want to write a quotient as a product? I give you a very, very specific one. You remember what it was? Anytime the denominator is something raised to a power. Is my denominator something raised to a power? Yeah, then you're going to cut half the work out by writing this as a product. It won't change your final answer, you're just going to get there with half the steps. So I'm going to rewrite this as e to the negative 2x times tangent of x. You with me? I guarantee you this is going to be easier doing it this way. My goal is to get the right answer. But my goal is to get the right answer with the fewest number of steps. Doing a step in your head is still a step. Don't skip steps. Just minimize the number you actually have to do. If I do it as a quotient, I use quotient rule, and then there's massive simplification, and my final answer is going to look very different because of all the simplifying. This won't have any simplifying. What I mean by simplifying is your final answer, you're going to do a ton of canceling. So, first times the derivative of the second. What's the derivative?
Secant squared.
Secant squared, good. By the way, don't write this down. I'm seeing this a lot lately. There's never going to be a time when you square the argument. There's no operation where you would ever square the argument. No. These are not even similar. If you put the square, no. That's okay. But if I put the square on the x, I'm only squaring the x. I'm not squaring the function. Word of operations. You've got the square in the wrong place. Okay? Plus the second, I can write d dx e to the negative 2x and then do all the work, or can we just differentiate that right now, out, just write it in front of us? The derivative of e to the thing is e to the thing times the derivative of thing. What's the derivative of thing? Negative 2. The derivative of e to the thing is e to the thing times derivative of thing. So you can write that as one sequence there. Now, do I have any common factors here? I think I do.
e to the negative 2. Minus 2 tangent.
Now what? Wave at it as you move on to the next problem. We are completely done. You cannot improve upon this. But wait a minute, you're saying, what don't you like? There's something you don't like, be honest. What don't you like? You don't like that, do you? Why? Why don't you like that? Is it negative? Is negative 2x a negative number? No. Negative 2 is a negative number. Negative 2x is not. Negative 2x is positive how often? Half the time. Oh, so leave it alone. That is the most simplified answer. Putting it down below is not wrong, but it's absolutely unnecessary. Negative 2x isn't negative. It's a variable. Until you replace x with a number, it can't be negative or positive. It's neither positive nor negative. Oh, you like that better? Leave it alone? Yeah, I'm a big fan of leave it alone. Is it wrong to put it down below? No, because that's the way the question was asked. So putting it down below makes the answer resemble the question, and that's actually a good thing. There's nothing wrong with that. But what if I got to do another derivative, or I got to evaluate this with my calculator, or anything else? We differentiated in one step, we factored in the second, we're done. We'd used quotient rule, we would have gotten an answer, but it would have been a few more steps, by the way. There would have been, and there would be major simplification and canceling top and bottom, because I'd have had e's in every position, they canceled. Now, if I do rewrite this, I want you to notice something. If I do rewrite this, do you notice anything? In quotient rule, isn't the denominator getting squared? It is. But things would have canceled, my denominator ended up being exactly the same. Who knew? This answer is absolutely acceptable. And so is this one. And if this is the one you came up with first, just do that. Okay? X to the negative 3, I'd put it downstairs. But 3 to the negative x, I would leave it alone because negative x is neither positive nor negative until I evaluate it. Okay, so sometimes we don't have to do certain things. All right. Okay, I want you to start this on your own. I'll jump in and join you in a minute. I'm going to go grab some coffee or something right now. So we use the limit to come up with our result, but we're not using the limit to do any of our derivatives at this point. We're using our results. Okay, product rule and chain rule, right? Chain rule, because when I differentiate the exponential function, I'm going to have a chain rule factor. But product rule takes precedence because it starts as the product of two functions. So walk me through. What's my first step going to be?
Cosine of x
Cos x
times e to the secant x times secant of x tangent of x.
Good. And there's my chain rule factor. Pretty clean. Second half.
E to the secant of x times negative sine of x.
Times the negative of, oops, times the negative of the sine of x. Okay. Well, clearly I have an exponential that's the common factor. I think that's a no-brainer. I have a bunch of trig-ish stuff here. Are there any identities or things I can use? And do you notice anything?
Can't you cancel?
What do you notice? What is cosine x times secant x? 1. Ooh, should I take advantage of that? Yeah. Do you want to write the product of three functions? No, you want to write just the tangent function. Then what? Yeah, that's way nicer, isn't it? Can I improve upon this? No. Now, for some strange reason, on a recent quiz, a lot of folks were taking things like tangent or secant and rewriting them as quotients. That is a never again the rest of your life do that. There's no time you will ever take something that's not a quotient and intentionally make it a quotient. You're going backwards. It is the extreme opposite of simplification. In fact, it's a wrong answer because if the answer is not a quotient, you can't write the answer as a quotient. The answer is 3, but I'm going to write it as 6/2. Why? Just because I feel like it. No, if the answer is tangent, you don't change it to sine over cosine. You're going the wrong direction. It's tangent. There is no quotient in my answer, so writing a quotient means I'm not done. So never go backwards. Now, if I'm doing a massive simplification, it's where you have the quotient of all these trig functions and you're just not comfortable. I said change everything to sines and cosines so you can recognize what combines and what cancels. But in the end, if your answer is not a quotient, don't write a quotient. Sometimes you have no choice. If I have 1 over a trig function, that is another trig function. That's always the case. And if my answer is just a trig function, then I rejoice because, that's nice. This cannot be squished together into something smaller. So this is the best I can do with this one. But again, 1 step for the calculus, 1 step for the factoring. Usually that's as much work as it should take. I had a funny question this morning. One of my Calc 3 people came and they were, the usual asking me, does this look right? You have to ask the question carefully because you don't want to make it sound like you want me to grade it before you turn it in. But I'll say I go, this is what it's supposed to look like. It's up to you to just double check the arithmetic. Then I pointed to one, I said, you skipped some of the algebra here. You have the result. I go, there's probably about 3 steps here that you really do need to show. And then they laughed, they said, actually it was about 15 steps. And I said, that's probably not good because I did a similar problem, showed them there was exactly 3 steps, but they showed me 2 pages of writing where they were going backwards and forwards and all over the map. There was triggish things in there. And they were unsimplifying and simplifying, and I had some fun. They got the right answer in the end, but they went way roundabout getting there. And I would prefer you not take extra steps if you don't need to, because you get lost. Plus, you might make a mistake anyway. So right now, if I have an exponential function in there anywhere, we know how to take the derivative. We know how to differentiate any of the trig functions at this point. We know how to differentiate anything polynomial-ish in nature. Okay, so therefore we can differentiate any combination of these things. Any questions so far? Okay, now see one that's a little bit beefier. How about if I said let's differentiate x cubed times e to the x squared? It's got just a little bit more going on. I mean, you see the e, you rejoice. Well, E makes us happy. It really does. Okay, this one's dying on me here. Okay, so first thing I'm going to write,
X cubed
times
e to the x squared.
e to the thing, and again, if you have to say it out loud, say it out loud. E to the thing, so therefore times the derivative of thing, which would be
2x.
2x. Okay, stop. First times derivative of second, but the derivative of second involved chain rule because it was e to a function, not just e to the x. As long as I get the chain rule factor, I'm good. There's nothing here to second guess or question. You can't memorize. You've got to do this over and over again. It's got to be repetitive until the point where it's automatic. Okay? And when it's automatic, then you're going to do the right thing 100% of the time. You won't think about it, and you certainly won't second guess yourself. Plus the second times the derivative of the first.
3x squared.
Is there anything else to do calculus-wise? I'm having some people keep doing the derivatives. So you've already differentiated the first. You're done with the derivatives completely. So now it is look for common factors. Because one of them is an exponential function, it's always going to factor out no matter what. But then the other stuff is x to power stuff. So I want to get that right also. So right now I have x to what power? I have x to the 4th on the left X to the second on the right, what's the common factor there? X squared. I have an exponential on both, and it has to be the same exponential. Now, what does that leave behind? Let's say it out loud. This was 2x to the fourth, correct?
Mm-hmm.
And I factored out an x squared, so what does it leave?
2x squared.
2x squared. I factored out an x squared, so it leaves
3.
just the 3. Now what? Every time I say it's a trick question. Now what?
Nothing.
Yeah, wave that, you're done. I say that because if you keep going, you're not going to improve upon this, so you might take a wrong turn. Okay? You reached my house, but you decide to keep going. This is it. Now, does it matter what order you write these terms? No, it's a product. Again, the textbooks more often than not will put the exponential on the last just because it reads pretty. I don't care. It doesn't make any difference. It doesn't make it easier. If I'm doing this on Desmos, I'm probably putting E last just because it's easier to type in, but it doesn't change the meaning at all. Okay? That's a perfectly good answer. Question. Now, this goes back to last week. I have f of g of x. Composition of functions, the most common type of derivative you're ever going to take the rest of your life. Right? You're not always going to do x squared, you might do function squared. You're not always going to do sine x, you might do sine of function. You're not going to do e to the x, you're going to do e to the function. Whatever. I want to differentiate this. Asking the question. True or false?
False.
You're working with people, you're at the LRC, right? You're at the STEM Center. You're working with people, and they're doing their derivatives, and they're telling you this is correct. And they're really insistent. And they're offering you free food if you go with them. It's a tough choice.
Having a great.
What do you think? True or false?
False.
I just did this. Do you remember what I said about the argument of a function?
Can never change.
It can never
Change.
change. Did we just change the argument?
Yes.
Yes. The argument of this function is g of x. I just changed it. But isn't there a g prime of x in the problem? Yes, there is. I'm doing f prime of g of x times g prime of x. In other words, this is e to the x squared times, if you will, the g prime of x. It shows up as a chain rule factor, not as a changed argument. Will people make that mistake? In calculus, that will be the single most common error made because it looks like the truth. It looks a lot like the truth. In fact, isn't there a 2x somewhere in this answer? Yes, it is, but it's a chain rule factor. The argument has to stay this throughout the end of the problem. It never changes. And it's an easy mistake to make if I don't practice enough. But once I get the hang of things, I realize, okay, whatever my function of u was, I have a new function of u multiplied by the chain rule factor. The chain rule factor doesn't become the new argument. That would never work. Okay. Any questions so far on this? We're pretty good on this? We'll do a little bit more, we'll take a break because the stuff we're doing in the second half, we need a little bit more time for the logarithm stuff. Let's see. All right. This is how I ask it on a test. I'll say y equals, tell me what dy dx equals. I have not called any of these a function yet, have I? I just said, it'd be like me giving you a number and saying, take the square root of this number. I never called it y equals. I just said, take the derivative of this function. Now I'm saying, let's call our function y equals. Now I want you to take its derivative. This is a pretty nasty quotient rule, you agree? Well, no, that's a very nasty quotient rule. Is that what you're going to do? No way. What are you going to do?
Tangent of x.
Divided by this? Wait, can you do that?
Yeah.
Should you do that?
Yes.
Oh, yes. Yeah, you guys are gonna get the hang of it really quickly. If you can make a problem easier before you start, we just made the problem easier. We are gonna do a fraction of the number of steps, and we're not gonna have to rewrite it. We're not gonna have to rewrite it as a quotient when we're all done. Ooh, we like that. You think? I'm not sure. So, I wanna differentiate that guy. So walk me through.
Tangent of x times e raised to the power of negative ex squared times the derivative of the exponent of e,
So what's this?
negative 6x.
Negative 6x. I always literally stop and take a breath right now. Just do a quick 2-second scan. Okay, good. I didn't lose anything. I didn't gain anything. You're not going to make a mistake here. But when you go too fast, something might get left out. So I'd say stop, take a breath. Is that right so far? Cool. Okay, let's finish. Plus
e to the negative 3x squared times secant squared of x.
times secant squared. Now, is there any identity I can employ here for the trig terms that I can somehow, no? Yeah, there's a Pythagorean identity. I can make secant squared into 1 plus tan squared, but that's not making it easier. I'm adding a term. It's going sideways, maybe even slightly backward. There's no help there. Leave it alone. Now, if both of these had a secant in them, yes, then I would factor something out. But I don't have anything in common, so just leave it alone. Now, do they each have an x in them? No. The only common term is the exponential. I don't think there's anything else in common.
Negative 6x.
So negative 6x, I'm definitely putting that in front. I think that reads better. Then what?
Plus secant squared.
Most people would probably like to write that in reverse order, just prettier. Would it be different if I wrote secant squared minus? Would that be a different answer?
No.
No. It might read prettier, but is it actually even an improvement? Not really. So therefore, leave it alone. Now, in the strictest sense, should this go downstairs this time?
Yes.
Yes, because 3x squared is always negative, isn't it? But it's still a variable. So I'd say leave it alone. It is not wrong to put it downstairs, and most people would, again, because then it resembles the original function, which, remember, you're going to use this answer probably to answer something bigger, maybe in a physics class, maybe something else. This is maybe the first step of a really big problem, so if I have to use this answer multiple times, maybe evaluate it, you always want it in the most useful form. And I can't tell you what that is without knowing the bigger picture. So I'd say leave it alone, but if you found a more useful form is to put the e in the denominator because of how it's getting used later, then you'd write it that way. This is correct. So if this is correct, leave it alone. Right? We don't want to take a chance on making a mistake. Everybody cool? All right, go ahead and hit the red button. We'll stop. Just press straight down.